everyone. In this video, let us discuss about the word embedding, frequency-based word embedding. So first of all, we should understand what is word embedding, right? So let me give you an example now. Say for example, you want to find out the meaning of a sentence or the meaning of a message that is sent by your friend in WhatsApp, right? So you want to find out the meaning in the sense like your friend has texted you in say in some other language, right? Actually that you do not know. So what do you do now? You type the same sentence in Google Translate and then you will try to get the meaning of it, right? Say for example, if you open Google and search for some articles on data science, and you can get hundreds of search results related to that. So what are these examples actually mean, right? So what is happening here? Text processing, right? Text processing. So as we all know, humans can deal with the text format quite intuitively, but provided we have millions of documents being generated in a single day, we cannot have humans performing all the tasks, right? So it is neither scalable nor effective. So how can we make computers to perform classification tasks, or say how can we make it to perform classification or clustering, right? So we know that these are generally insufficient at handling and processing strings or text for any fruitful outputs, right? So a computer can match two strings and tell you whether they are same or not, right? So a computer can match two strings and tell you whether they are same or not. But how do we make computers tell you that whether it is the same or difficult? Say for example, you want to make a computer to understand that apple is a tasty fruit, right? And also at the same time, apple is a fruit that can be eaten, but it is not a company, right? So when we talk about apple, it could be one is that it could be a fruit, or else it could be another. I mean, what I try to say is it could be a company, right? So how do you make the computer to understand whether you are looking for fruit or company, right? So the answer to all these questions lie in creating a representation for words that capture their meanings. Basically, you to capture their meanings, semantic relationships, and different types of context, etc. Right? So this is what we are going to see over here, right? So now let us try to understand what are word embeddings, right? So word embeddings are the text converted into numbers. So as I told you, machine is not able to understand the text. So it has to be converted into numbers. And there may be different numerical representation of the same text, right? So I think that is clear that why we are using this, why we are going ahead with this word embedding technique, right? So when we talk about machine learning algorithms or deep learning architectures, they are capable of processing strings or plain text in raw form. They require numbers as inputs to perform any sort of job. Say, for example, when you deal with the machine learning, we used to do one-hot encoding technique, right? And with a huge amount of data here, when we have it in the text format, it is imperative to extract the knowledge out of it, right? So like, for example, you purchase some product from say a company A or B, and you are writing reviews about it. And now the company has to identify whether the product has really satisfied the customers or not. So this basically we call it a sentiment analysis, right? So a word embedding format generally tries to map a word using a dictionary to a vector. So the sentence can be broken down to have a clear view, right? So let us understand word embeddings are the text converted into numbers, and there may be different numerical representations of the same text. So a vector representation of a word may be a one-hot encoded vector, where 1 stands for the position where the word exists and 0 everywhere else. So how can I understand this? Say for example, I have this dictionary. Word embeddings are converted into numbers, right? So for this numbers, I have to write it, right? So what I can say 0, 0, 0, 0, 0, 1. In case if I want to write for converted, it is going to be 0, 0, 0, 1, 0, 0. So basically, word embedding is a way to convert a piece of text in a numerical format that our machines can read. So there are different types of word embeddings. One is frequency based and another one is prediction based embedding. So in this video, we are going to discuss about frequency based embedding, right? So when we talk about frequency-based embedding, there are 3 types basically. One is count vector, the second one is TF-IDF vector, and the third one is a co-occurrence vector, right? So let us try to understand one by one. So when we talk about frequency modeling, first let us try to understand what the count vector means, right? So what are we trying to understand? What the count vector means. Say, for example, there is a corpus, C of D documents. So that's why I have written D1, D2, D3 up to DD. And there are N unique tokens extracted out of the corpus C. So the N tokens will form our dictionary, and the size of the count vector matrix will be given by D cross N. So here each row in the matrix M contains the frequency of the tokens in document, right? So how can I understand this little more clear? So let me give you an example now. Say for example, so I'm writing a sentence now. He is a lazy boy, right? And she is also lazy. So we are writing about someone saying that he is lazy boy and she is also lazy, right? So this could be a sentence. And the next one, what I'm going to write is Neeraj, or you can write any name. So I'm writing Neeraj is a lazy person, or like something else, right? Okay. I can use anything. You can write anything over there. Okay, let it be Neeraj. Okay, nothing wrong. If there is any Neeraj over here, then only we should worry about it, right? Then also don't worry about it. This could be some other Neeraj, right? So Neeraj is a lazy person, right? So now the dictionary creator may have a list of unique tokens. So what are the tokens here? He is a token, she is a token, lazy is a token, boy is a token, Neeraj is a token, person is a token. So here I can say that D is equal to 2. Why do I say D equal to 2? Because there are 2 sentences, right? So I'm saying that D is equal to 2 and N is equal to 6. Because what and all I'm going to consider? He, lazy, boy, she, Neeraj, person, right? So what do I get now? I'll be getting a count matrix of size 2 cross 6, right? I'll be getting a 2 cross 6 matrix, right? So let us understand this. Okay, so let this be D1 and let this be D2, right? So I'm going to write it over here, D1 and D2. And here I'm writing he, and here I'm writing she, and here I'm writing lazy, boy, Neeraj, right? It could be person, right? I do not have. Okay, so let me erase this. Let me write this, right? So I'm going to write it as he. I'm writing she. I'm writing lazy, boy, Neeraj, and then I'm writing person, right? Okay, so first I'm going to consider what? D1, right? So I'm going to consider D1 now. So in D1, what I can say, he is there for one time, she is there for one time, and lazy. And here also I can see lazy. So that's going to be 2. And boy is 1. Basically, Neeraj is also 1. And person is also 1, right? Oh, sorry. Neeraj is not there, right? Because we are talking about D1. So when you talk about D2, what it is going to be? There is no he, there is no she, there is one lazy, and then there is no boy, Neeraj, and person. This is what I'll get. So now a column can be understood as a word vector for the corresponding word in the matrix. Yeah. So here, if I write lazy, I can write it as lazy. I can write it as 2, 1. And here the rows corresponds to the documents in the corpus and the columns corresponds to the tokens in the dictionary. So let us try to understand. Rows correspond to the documents in the corpus, right? So how many, right? So I hope that is clear, right? And here the rows correspond to the document in the corpus and the columns correspond to the tokens in the dictionary, right? So the second row here, I can say that D2, in the D2, there is only once I have lazy. And there is Neeraj only once, person also only once. Now there could be a few variations over here. The way dictionary is prepared by, right? So in real world applications, we might have a corpus which contains millions of documents. And with this millions of documents, we can extract hundreds of millions of unique words. So basically the matrix that will be generated like this, will be a very sparse one and inefficient for any computation. So an alternative to using every unique word as a dictionary element would be to pick, say, top 10,000 words based on frequency and then prepare a dictionary. Do you understand what I mean over here? We may have a corpus which may contain millions of documents. And with millions of documents, we can extract hundreds of millions of unique words. So the matrix that will be prepared like above will be a very sparse one and inefficient. So what do we do as an alternative? Like we will be using every unique word as a dictionary element would be to pick, say, 10,000 words based on frequency and then prepare a dictionary, right? So here the way count is taken for each word. So we may either take the frequency, that is the number of times the word has appeared in that particular document, or the presence, which means like has the word appeared in the document to be the entry in the count matrix here, right? So that is what being represented over here, term 1, term 2, term 3, right? So this is basically a document vector. So there are 8 documents and here there are 8 terms, right? So this is about count vector. So the next one is about TF-IDF vectorization. So this is another method. This is also frequency-based method. But what is different from the count vectorization is that it takes into account not just the occurrence of a word in a single document, but in the entire corpus. So is it rational? Right? So that's what we are trying to understand. Say there are some common words like is, the, right? So these appear to quite frequently in comparison to the words which are important to a document. For example, a document A, there is a word called a Lionel Messi is going to contain more occurrences of the word Messi in comparison to other documents. But common words like the, etc. are also going to be present in higher frequency in almost every document. So ideally what we want to do, what we want is to downweight the common words occurring in almost all the documents and give more importance to words that appear in subset of documents. So how does this TF-IDF works is it penalize the common words by assigning them lower weights while giving importance to words like messy in a particular document. So let us understand. So here we will be using TF. TF means the number of times the term T appears in the document divided by number of terms in the document. So basically it denotes the contribution of the word to the document. That is, the words relevant to the document should be frequent. So if a word has appeared in all the document, then probably that a word is not relevant to particular document. But if it has appeared in a subset of documents, then probably the word is of some relevance to the documents present in. Right? Fine. So let me take an example now. Right? Let me take an example now. Let me type it up. Say I'm writing like this is about puppy, right? So the second sentence what I'm writing is this is about say dog or cat or something like that, right? Anything you can take, right? Fine. So here in the document one is this is about puppy. This has you have to see that like how many times it is being appeared, right? So how many times it is being appeared. So what I'm saying, TF means number of times the term T appears in the document divided by the number of terms in the document. So totally there are 8 words, and here I can say that like this in document 1 has appeared 1 by 8. In document 2 has appeared 1 by 5, right? So it denotes the contribution of the word to the document. That is, words relevant to the document should be frequent, right? So in case if I try to find out IDF, which is equal to log of capital N by small n. Capital N means number of documents and small n is the number of documents a term T has appeared in, right? So when I find out this when I try to find out this IDF, which is nothing but a log of capital N divided by small n, right? So what is this capital N basically means? This is the number of documents, and this is basically the number of documents that term T has appeared in, right? So now in case if you find out the value for this, this is going to be log 2 by 2, which is going to be equal to 0, right? So this is how this is being done, and then TF into IDF, that will give us the TF-IDF, right? I hope this is clear, right? So this is how the TF-IDF basically work. And then now let us understand the co-occurrence matrix with a fixed context window. So now similar words tend to occur together and it will have similar context. Say for example, apple is a fruit, mango is a fruit. Apple and mango tend to have a similar context, right? Basically both are fruits. So before understanding like how the co-occurrence matrix is constructed, let us try to understand two concepts over here. One is about the co-occurrence. Okay, so you have to understand about co-occurrence. And the second one, what you have to study is about context window, right? So you have to study about a context window. So what is co-occurrence? For a given corpus, the co-occurrence of a pair of words, say W1 and W2, is number of times they have appeared together in the context window. I hope I'm clear, right? Co-occurrence, co means together, right? Together occurred. So which means that I'm taking a pair of words, say W1 and W2, number of times they have appeared together in a context window. So what is context window? Context window is specified by a number at the direction. So what does that mean? Say for example, I say context window of 2. So what does that basically mean, right? So let us try to understand that, right? So let me take a whiteboard now. See, for example, I'm saying like a quick brown fox jumped over the lazy dog. So now you can see here, say for example, here, these are two context window for the word fox. And for calculating co-occurrence, only these words will be counted. So in case if I am trying to find out for over, what will happen? If I want to find out for over, these two will be considered, right? So basically fox, jump, and then the and lazy, right? So now let's take an example corpus to clearly understand what this what this basically means, right? So this is what we are going to understand, right? So let me say that in the corpus, what I have is he is not lazy. He is intelligent, right? And he is smart. Okay. Now let us try to understand what this co-occurrence matrix by seeing some examples over here. So you can see some boxes over here, red box and blue box over here, right? So red box is that how many number of times he and is have appeared in the context window 2, right? In the context window 2, and can be seen that the count turns out to be 4, right? So how I can tell that? Say he is not lazy. Okay, let me show the let me show you that, and I'll make you to understand. So you can see that he is not lazy, he is intelligent, and is he, because basically I'm asking for is he is, right? So he is. So what we can find from here is red box tells us that the number of times he and is have appeared in the context window 2, and it can be seen that the count turns out to be 4. And here the word lazy has never appeared with intelligent. Here you can see that, right? The 0 corresponds to lazy as well as intelligent. So we are trying to see that lazy has never appeared with intelligent in the context window, and it has been assigned to 0, right? So what is this co-occurrence matrix? So what are the variations over here? Let's say there are V unique words in the corpus. So vocabulary size will be equal to V. So the columns of the co-occurrence matrix form the context words. So what are the different variations over here? A co-occurrence matrix of size V cross V. Now for even a decent corpus, V gets very large and difficult to handle. So this architecture is never preferred in practice, right? A co-occurrence matrix of size V cross N, where N is a subset of V, and it can be obtained by removing irrelevant words like stop words, etc. So this is still very large and present computational difficulties, right? So, but remember that this co-occurrence matrix is not the word vector representation that is generally used. Instead, this co-occurrence matrix is decomposed using techniques called as PCA, SVD into factors, and then combination of these factors form the word vector representation, right? For example, you are performing PCA on this matrix of size VXV, right? So you'll be getting V principal components. So you can choose K components out of these V components. So the new matrix will be of the form V cross K. So a single word can be represented in V dimensions, will be represented in K dimensions. So what PCA does at the back is it decomposes co-occurrence matrix into 3 matrices, right? And U, S, and B, where U and B are both orthogonal matrix, right? So you can see that both are orthogonal matrices. So here it is the dot product of U and S that gives the word vector representation, and V gives the word context representation, right? So now let us try to understand the advantages. So basically it preserves the semantic relationship between words. That is, the man and women tend to be closer than man and apple. That's very obvious. It also uses SVD at its core, which means it produces more accurate word vector representations than existing methods. And it uses factorization, which is a well-defined problem and can be efficiently solved. And it has to be computed once and can be used anytime once computed. So in this case, we can say that in the sense it is faster in comparison to others. See, what are the disadvantages of co-occurrence matrix? So it requires huge memory to store the co-occurrence matrix. But this problem can be circumvented by factorizing the matrix out of the system, like Hadoop clusters and all, right? So these are the types of frequency-based modeling. Basically, we have covered count vector, we have covered TF-IDF, we have covered co-occurrence matrix. Hope this is clear to you. Let us meet in the next.